Okay, hi, let's get started. There was this question about Chapter 4, MJC Physics 142, Chapter 4, Part 2, Problem 13, for those of you who it matters. Or you can just look at the problem, and it's a neat problem. Here we go. We have a block, and somebody starts pouring sand into the bucket until it just starts to move. So there's actually two parts to this problem right away. This is the key. Sand is added until it just begins to move. So we are in a situation where we're not able to move the bucket. And then we kind of reach a sort of tipping point where it does move the bucket. If you read the question carefully and pause, and feel free to do that. Okay, assuming that you paused and read the question, the key here is that there's a static friction, which is higher than kinetic friction. So we have two things going on. Kinetic friction is kind of, pulling this way, if you will, and prevent, because this block has friction. So let's actually draw the diagram separately. Here's the diagram of the block. There's the force of gravity due to the block. There's the normal force, because for each action, there's opposite reaction. So, the 28-gram mass pushes on the table, and the table pushes back, and that's called normal force. It's perpendicular to the surface. There's also some friction here. And even though the bucket is pulling down indirectly, like so, let's call this T1 and kind of just leave it here, pointing like this. Even though the bucket is pulling down indirectly, it's not enough to overcome the force of friction. And I'm going to call it force of static friction, S for static and FR for friction. So that's what's going on. And for the longest time, the sum of sum of all forces in the, if you will, the x direction is the force of static friction, right? Plus the whatever tension one or the weight of the bucket is providing. And it's not moving because, I get it to just the right point. There's just enough sand poured into my bucket and it's still not moving. And just before the tipping point comes, I'm still zero, right? Because the sum of all, the net sum of all forces is zero. So what we have to do is kind of think about what that means. That's one. That has to do with static. And then the next one has to do with movement. And, it does start moving because this friction goes down. Kinetic friction is less than static friction, if that's a concept that you're clear on. Once things start moving, there's not as much friction between the two surfaces. So that's why now, T1 wins and we start moving. So we'll get into that. Let's first solve the first problem. So we have to figure out what the force of friction is, right? What's this part? But before we can figure out friction, we have to figure out everything else, because one of the things we know is that the force of friction, static or otherwise, depends on the coefficient of friction times the normal force. If you're not familiar with that, it's worth looking into and understanding how normal force, goes along with a friction constant to prevent movement. But that means two things. Force of friction, static friction, is equal to, you just need the static coefficient with the normal force. For force of kinetic friction, you just need and this is just my convention, you don't have to write it the same way. You need the kinetic coefficient. So here, let's talk about the normal force, right? The sum of all forces in the y direction over here, right? I'll undo that. Is basically normal force plus, because the box is neither moving up nor down. It's perfectly balanced, right? So the normal force, that's equal to zero. So that force of gravity, that's pretty obvious. Mass times acceleration due to gravity is equal to zero. Normal force. And so if the normal force is going up and that's positive, and gravity is going down and that's negative, so that's like 28 kilograms times 10 meters per second square. And because gravity is negative, I'm going to put a negative there and positive here. That's zero. So F of n is basically equal to, let's do it step by step, minus 280, which is equal to 0. And F of n normal force is equal to actually 280, which makes sense. If the mass is pushing down on the table with 280 newtons, the normal force is pushing up with 280 newtons. And that's really the only way to have no movement, when the net forces equal 0. Okay, so that was a lot of work for very little, something that's probably obvious to everybody. But we now know that the normal force is equals to 280 newtons, 280 newtons. So that's useful. So now we say, oh, okay, we can just plug it into the assumption we had that force of friction is equal to the mu and normal force. And we take it from there. Force of friction is, so the static friction they gave us right here, because nothing is moving. So that's it. So 0.450 times 280 newtons, right? And that'll give us something like 160, I think. 280 times 0.45. No, it's 126. So that's 126 newtons. Now we know what we're working with, right? So let me just erase this and just write. This is 126 newtons. This is 280 newtons. And this is 280 newtons. And those cancel out. I'm going to remove all this stuff. So if nothing is moving in the x direction, basically if I have no pull in this direction yet, because I've not reached the tipping point, I'm just adding stuff, that means the tipping point can only be reached once I go over 126. So I already know what T1 should be. It should be 126. But if I was to show it, very nicely, then I would be saying that the force of static friction here is 126, right? And I don't know my T1, but I know it's not moving, so it should be 0. So the T1 is equal to, and they're in opposite directions. So if you say force of static friction was in opposite direction, when you take it over to the other side, you just get 126 newtons, negative becomes positive. Add 126 to both sides. So T1 should be 126 newtons, which is kind of obvious, but you can show the math for it. So now you know all these things. So let's clean up a little bit. Okay, so you know all these forces. T1 is equal to 126 newtons, and all these other things. Okay, so now about adding sand to the bucket. I was adding sand to a bucket that was providing a force of, by itself, it was providing a force 1.35, multiply that by mass times acceleration being 10, so 1.35 kilograms times 10 meters per second square, and that's equal to 13.5 newtons, right? So the bucket by itself was providing 13.5 newtons. And I kept putting in stuff, I kept putting in sand until it reached 126 newtons. That's when I was perfectly balanced, right? That's when I was at the tipping point. So how much weight could the sand have had? 126 minus 13.5. So the sand could have weighed 126 minus 13.5. That's 112.5 newtons. And if you divide by 10 meters per second square, because you're going back to the math, force equals mass times acceleration. The force of the sand is 112.5 newtons. You don't know the mass of the sand. The acceleration is 10 meters per second square. Mass of sand. So then you know that it's basically just 11.25 kilograms, which if you round it up, 11.3 kilograms. That's how much sand we would have to add to provide a total force along with the bucket, which balances out against the friction, right? This 11.3 plus this 13.5, sorry, that was wrong. This 11.3 plus 1.35 kilograms, which was the bucket, together, they make up 126 newtons. That's kind of what I wanted to say. So that's all good. Now we know that. So the first question was calculate the mass of the sand added, and I said about 11.3 kilograms, 11.3 kilograms, and yeah, that seems to be one of the right answers. So that's good. Let's erase this stuff, okay? Keep this a quick way. Okay, now let's work on the next part of the problem. The next part says, what's the acceleration? So what they're saying is maybe you just went one sand grain over, right? Like you went over too much. Not by a lot, just by enough that it's like 126.0001, something like that. You went over. Now, what that changed was your system started moving. And the second it started moving, your friction decreased from 0.45 to 0.320. So, this force decreased by a lot because the friction is now different. So the friction for the kinetic aspect is now 0.320 instead of 0.450 like before. And the normal force hasn't changed, that's still 280. So if you do that, so now your new force of friction is 280 multiplied by 0.32, which is 89.6 newtons. I mean, that's a far cry from how much force. So earlier you had 126 newtons when you were static because the friction was very high. Now you can only provide 89.6 newtons. So if you look at it, the system pulling this way, right? It's now only able to do this much, and you can redraw it. And the system at the bottom is still pulling at 126 newtons, right? Or you can redraw it like 89.6 newtons. You can call it positive, up is positive, down is negative 126 newtons if you wish. And you can say that this is, this is not the same, or actually let's do it another way, just for fun. Let's call this positive and that negative. And you can say, well, when the sum of all forces in the y direction was 0, there was no movement. Mass times acceleration had no meaning because there was no movement. But now there is a force. There is a force, 126 minus 89.6, because this is pulling down harder than this is pulling up. So now we can figure out an acceleration. So if we look at it, 126 minus 89.6. There's 36.4 newtons of force downwards than there was before. And so now we want to find the acceleration. This is not the acceleration due to gravity. This is the acceleration due to this net force, okay? So we have to figure out what our mass is. Now, if you just think that the mass is the sand, or the mass is the bucket, or the mass is the sand and the bucket, you're not seeing the big picture. The mass is actually this block, and this rope and pulley are considered massless. That's just assumed. It's really the block and the bucket which are connected. They're both being pulled down. So really, this equation looks like 36.4 newtons of force pulling downwards on the mass of the bucket plus the mass of the sand plus the mass of the block bucket, right? And then it's accelerating. So if you take that into account, and you're like, okay, I had roughly, I don't know, overall, I think this added up to 12.6 kilograms, and if that doesn't make sense, you can just write individually, and you can say bucket was 1.35 kilograms, sand was roughly, how much was it? I lost it in that. 11.3 kilograms, that's fine. And the block was, I don't know, 28 kilograms, right? Just add it all up and you'll end up with 36.4 divided by something like, let me see, kilograms plus. Something like 36.4 over 40.6. So this is in newtons, this is your kilograms, that's your total mass. So now you have to find your acceleration, which should be roughly 36.4 divided by 40.6, 0.896 meters per second square. You can round it off to 0.90 meters per second square. And that's kind of what I ended up with. I think the right answer is 0.88. Maybe I should have used 9.8 meters per second square. When I was doing all of this and finding my weights, I just used 10 meters per second square. Maybe there's another small error, but pretty close to the correct answer right here about how the system will accelerate. System being everything together, the block, the bucket, the sand. And that's why the total mass was done this way. Okay, I hope that helps. Bye-bye.